Hi everybody, it's Tim Hagan and welcome to today's webcast presented by PowerTest. And again, my name is Tim Hagan. I'll be today's moderator. And as you have any questions as the webcast goes forward, I see a number of you have sent a quick hello to myself. Thank you, and we'll get started here. So if you have any questions, again, that's where we'll collaborate with you in the Q&A panel, so we appreciate your time today. This is a monthly webcast that we do every single month at PowerTest, so we appreciate you joining us today. So what I'd like to do is introduce today's presenter, Rick. Rick, give a brief introduction of yourself.
Hi, how is everybody? My name is Rick Ballo. I've been working for PowerTest for approximately 6 years. I'm an international sales manager for PowerTest, covering the Middle East, the Far East, Australia, and Africa. My background is mechanical engineering and sales, so I'm glad to help out today.
Thanks, Rick. So at PowerTest, we make it better, and our mission here at the company is to make it better not only for our customers, but for our employees and also for the community. Now today's topic is the basics of engine test cell water circuits, where we make testing easy. So today's agenda, we're going to cover 4 main areas, and Rick will be taking us through this, and I'll be turning over the controls to him here in a second. You know, first of all, why do I need a water circuit? Second, what does a water circuit actually do? What's important to know? And installation variations. As we go through today's presentation, one of the things I want you to realize is that I will be checking the Q&A panel as the presentation is going forward. And I'm just now about to make Rick the presenter. So Rick, you are now in control. And show your PowerPoint, and we're off and running. So again, if you have any questions today, feel free to put those into the Q&A panel, and we should be good to go. Take us away, Rick.
Okay, so why do I need a water circuit? I think the number one thing I've got for everyone is it is probably the least misunderstood portion of a dyno system. And when people call into me or my compatriots at PowerTest, the first question is, I need a dyno. And what people do not realize is the added components required to build a dynamometer system. So I'd like to run through a couple of things. Number one, when you're testing a diesel engine, that's typically the use for a water brake dyno or for any dynamometer in our field. You can be testing this engine for anywhere from 1 hour up to 48 hours and sometimes longer for marine engines. So you've got to have a method of removing the heat from the engine and the dyno, cooling the water back down, and reusing it and recycling it. So it's by far that's the biggest issue with that. So I think the other thing is basically when you're purchasing a dyno, it is not like buying a power tool. There is significant infrastructure that's involved in the purchase of a dynamometer system, and that's where the water circuit comes in, including the pumps, the cooling tower, the water reservoir, and all the valving. So it's significant.
Hey Rick, are they the only load device that needs a water circuit?
No, water brakes are really one of 2 devices that need water circuits. So water brakes is one style of load device for loading an engine. Another device that is used for loading engines are water-cooled eddy current dynos. Significant difference between the 2. Some of our competitors sell those. We sell some water-cooled eddies. Definite price difference between the 2 systems. I think the biggest thing is what people have to understand is in a failure mode, if you lose water when you're operating a water brake, basically what happens is you have no load on your engine. If you lose water when you are cooling an eddy, you'll burn up the eddy because the water is the thing that's carrying away the heat from the eddy that's creating the load.
Okay, great, thanks.
Yep, thanks. All right, I'm going to move on to the next page. What does a water circuit do? Water circuit basically is designed to remove the heat from not only the dyno, the water brake dyno, but also from the engine. You've got to take that into consideration when you are sizing a water circuit. So if you call me up and say, Rick, I want to test a 1,000 horsepower engine, and I'm going to need a cooling circuit or a water circuit for it, basically what I'm saying is I not only have to remove the heat from the water break, but I've also got to remove the heat from the engine. So the water circuit is providing cooled water to the engine and the dyno, and via pumps and valves and filters, and also carrying away and cooling the hot water through the use of a cooling tower. As we go further into this, I'm going to explain a couple of different circuits. So we're really covering generic portions of this now, but later in the webinar, we're going to be walking through actual circuits so you understand how these function. And we're moving on. Major components of a water circuit. So what you're seeing right now is basically a very generic view of a water circuit as it would appear on grade. So it's you're probably seeing my mouse move, I'm hoping. You're seeing over here, this is a cooling tower. This line going across here is the grade or the floor of your facility. Down below is a water reservoir. Here is a engine dynamometer. Here is the engine under test. These are all the cooling requirements, which we'll go over a little later for the engine. And this is a pump right here, this symbol, and this is a pump over here for this symbol. So we'll move on from here, and we'll start breaking it down. Water reservoir. Water reservoir is basically, typically, a storage container that is mounted below grade. And the reason why it's mounted below grade is because typically all of the major components, the dyno and the cooling columns, are gravity drained. So with the purpose of that, we can easily have water drain through standard drain pipes in your floor below grade, drain over into what is considered the hot side of the reservoir, which is denoted here in red. And as it walks through the cooling tower circuit, that water is placed over in the side that's the blue area, and that's used for recycling through the engine and the dyno. So it's divided into two sections, as you can see, and we'll walk through that a little bit later. In essence, what's happening is you can see there's a small opening at the bottom of the a wall that separates the hot side from the cold side. And in essence, what that's doing is that is allowing the hot water to be tempered. It's coming out of the engine dyno at about 160 plus degrees Fahrenheit. We don't want that water that hot to go into the cooling tower, so through the use of this small opening at the bottom, we can temper the water to a lower temperature, which is typically in the 120 degree F temperature range. I think we've gone through everything on this page.
Well, and Rick, one of the things, how do you go about sizing a reservoir?
Oh, that's actually a good question. So typically the sizing of the reservoir is dependent on what you're testing. And if I go a little further with that, there are pumps that we're going to see in a little while that are supplying water to the engine, to the dyno, and also to the cooling tower. So if I take the flow rates of all those pumps and add them up, typically our reservoir size is about 5 times the total flow rate of all the pumps. And that's just an average that we typically use for sizing. It works out very well. So if you've got 1,000 GPM of flow rate, or that's approximately, let's call it 4,000 liters per minute, you are going to have a 5,000 gallon or 20,000 liter total size reservoir in your system. Thanks for the question.
Sure.
Cooling tower overview. So this is another one of the major portions of the system. You can see the picture up in the right-hand corner. This is an installation of multiple cooling towers. What does this do? The cooling tower is a device that is designed to remove the heat via evaporation from the water. So what's happening is, as you can see in this, in fact, I'm going to zoom in if you don't mind. There we go. So what's happening in the system is here is this underground reservoir, in essence, and I've got a pump system that is lifting water up into the top of the cooling tower. The water is being gravity drained back down through this large pipe into the cold side. While the water is gravity drained over some media, a fan is blowing air across it, and it's the fan is carrying off heat via evaporation. And the best way I can describe how a cooling tower works is what an associate of mine told me is, put your finger in your mouth, lick your finger, and blow on your finger. And when you do that, your finger will feel cool. And that is the science of air movement carrying away heat based on the moisture content on your finger. So that is the way a cooling tower functions. It's just through that method. And let's zoom back out again. I think I've covered everything on this slide. Next question, and I wanted you guys to see, or ladies, I'm sorry, typical setups. And what you're seeing is some of our dynos in operation with various engines. These happen to be CAT engines. The engine on the right-hand side is about 4,000 horsepower. That's a C175-20 CAT engine. Extremely large. This is in the range of 40,000 pounds or 20,000 kilos. What's important? The most important thing is to remember that when you are producing power with an engine, if the engine is rated at an output of, let's say, again, 1,000 horsepower or 750 kilowatts, in reality, the engine is creating quite a bit more power. That is only the power that is being distributed through rotational energy out of the back of the crankshaft. The balance of the power created is really burned up in heat. If I look at diesel engines right now, diesel engines at the best case are about 45% efficient. In other words, 55% of the power or energy created by that engine is being dissipated as heat in some way, shape, or form. If in the same vein, if you look at a petroleum-based engine, in the best case, we're dealing with about 30% efficiency for an efficiency on the system. So number one, when I look at these engines, you can see the connections to the cooling system over here on the left-hand side. So we've got the water system connected. You can see over on the picture on the opposite side, you can see the turbocharger, the exhaust connections, and also the turbocharger cooling. So it's there's a lot of things that get involved in the engine circuit. So I am also not only trying to remove heat from the water circuit or the water jacket on the engine, but in most cases on modern diesel engines, is I also have to remove heat from the turbocharger circuit, which is the next slide we're going to get into.
Hey, Rick, do you have time for a question?
Sure.
Miguel asked a great question. The wall in the tank did not go to the top of the tank, so the water can flow from hot to cold. Is that right?
That is correct. And in reality, that's a barrier to separate typically the hot water from the cold. So and we're going to look more at that when I get into the circuits themselves later in the presentation. But that is true. The hot water is basically separated from the cold water, and further, typically the hot water side is 1/3 of the total volume of the total reservoir. So the cold side is 2/3, the hot side is 1/3.
Right.
You do have that hole located in the bottom for the passage of the cool water to temper with the hot water, as I indicated. Does that answer the question?
Yep. Thank you.
Excellent. That's perfect. Okay, so now we're moving on to one of the least understood portions of the system. We've got not only jacket water that we are taking care of, so we've got to remove the heat from the engine jacket water, which everybody's aware of. Typically, that is taken care of in a vehicle by the radiator or the rad. We've also got turbocharger cooling. So of that, there are two types. And what you're seeing in this picture is you're looking at what we call a CAC, or a charge air cooler, that is located over here, which is connected to the engine turbocharger, both the inlet and the outlet of the turbocharger. And what the purpose of this is to cool the air prior to entry into the inlet manifold of the engine. So we're taking the air that's heated by the turbocharger, cooling it down, and then presenting it back to the intake side of the engine. two systems are produced like this. I just went through the charge air cooler, or as they say internationally, that is typically called an intercooler. So, and I noted on the slide that's air cooling. And the second method is called aftercooling. And the aftercooling is doing the same thing. It's a method of cooling the turbocharged air prior to entry into the engine. The difference is there's an integrated heat exchanger built into the engine, and that heat exchanger is cooled by water. So we are taking water from our water circuit, and we are flowing it into the engine-mounted heat exchanger and removing the heat from the air prior to entry into the intake on the manifold on the engine. I hope that breaks things up for people relatively well. Turbocharger circuit cooling is a little bit misunderstood. People say, oh, we don't need it. I can tell you this I've had a lot of experience with this. If you do not use turbocharger cooling and you are trying to test to meet the standards as given by the manufacturer, if you do not use turbocharger cooling, you will not be able to reach the maximum output that is required on the test specifications. I've run into this with a lot of customers that have not bought charge air coolers that are doing, their customers may be a mine, etc., and they require testing directly to the specs of the manufacturer. So if you decide not to do that, either charge air cooling or after cooling, understand that you may not be able to reach the capacity of the engine in power and performance. Hold on one second. There we go. Dynamometer. Dynamometer, and number one thing is this is actually kind of a cool picture. In fact, let me blow this up for you because I can kind of talk over it while we're discussing things. This engine is approximately 8,000 horsepower. This is one of our largest dynos. This is the H36 series. This is a marine application. Typically, when you tip the scales at 5,000 horsepower or higher, typically these are marine applications used for naval shipping, tugboats, etc. But in this situation, it's a perfect picture of the dyno in application. You can see there the way they've got their water circuit and their exhaust system. So it's their water circuit, everything is connected below grade. They've got basically removable decking that they can access all of their plumbing. What you're seeing here on the right-hand side is the discharge system from the dyno, and that is heading down to the water reservoir, so you're kind of seeing this in real life. This pipe here is the inlet to the dynamometer itself. So I'll back out again, and we'll discuss this view of a dyno. So what's happening is a dyno is basically rotors and stators, and what's happening is we're introducing water into the top of the dyno. Meanwhile, as I think everybody is aware, this is the shaft, and the shaft is rotating at the speed of the engine. These two devices, you can see here, it's white and then it's turning into red. These are the rotors in the dyno, and those are spinning. And meanwhile, the stators, which is the plates on either side of this two-rotor dyno, are stationary. So what's happening is the water is trying to escape, and it's got to pass by the rotors and stators, the spinning rotors and the stationary stators, and try to escape. As the water flow increases, the load is increasing on the dyno. As the speed changes with our control system, and that's a different webinar, but we can vary the load and hold constant load based on changing speeds, etc. So it's we have that ability, but it's this is the heart and soul of a dyno, and this is really the major requirement for the water circuit. I cover everything here. Yep, obviously it's the device that covers the load. Water and flow rate and temperature differential affect the loading level. So we just discussed that. So it's as the water flow rate into the dyno changes, and that can be accomplished by either a variable speed pump, or in our case, also we do use variable speed pumps, but we also use a servo actuated load control valve. we can vary the load on each of the systems. I'm going to move on here. How are these systems used in practice? Now, this is probably going to be the more educational portion of this presentation. As you can see, cooling tower, pump system, and dyno in application. What we're going to do is we're going to review some water circuit variations, and I'm going to go through the most basic water circuit. I'm going to go through what is by far the most typical water circuit with a cooling tower. I'm also going to go through the last item, which is a cooling circuit with above grade or separated water storage, and we'll see what I'm talking about as I get into that. Basic water source circuit. What this is let's walk through this once. Here is the dyno as it's sitting on the system. Here is the engine under test, and we'll see that a little clearer in a little bit. And meanwhile, what's happening with the water? So the water is coming in from either a city source or it could be a pond, for example, if you've got a cooling pond, and that water is filtered, and a portion of it is flowing into the dyno, and meanwhile the other portion of the water is flowing over to the engine cooling accessory. So that is going to be, for example, the water cooling column. It could be a charge air cooler, or it could be an after cooler cooling column. So that water is obviously processed through the engine or through the cooling system, and that is basically dumped or returned to, it may be the gravity drain, which is our standard utilities in our house. It might be a floor drain back to the pond. It might be to a pump system. But what I'm really trying to say is the water that's being used from the cool water source is not going through any cooling method. It's not being stored. It is just being dumped. I can say typically this is not the norm anymore. This is just people being concerned with resource management. It's not the most efficient system in the world, and it's relatively inefficient. So you are not reusing and you're not recycling the water that you're processing through the system. Very, very basic system here. Let's move on to what we call the standard system. Standard or the typical water circuit. Now what you're seeing is this system is inclusive of a cooling tower. Here is that reservoir below grade. And I remember someone had a question before about the water storage, and we're going to walk through that circuit in a second. So it's I'll get back to that. But in essence, we've got the hot water side, the cold water side. A pump is pulling water up and discharging it into the dyno and the cooling system. In fact, I believe, there we go. So now we've got, through the miracle of modern animation, you now have cool water being pulled up by the pump, going through a filter, and at that point it is being split off. And it is split off to the 3 engine accessory cooling systems and also to the engine dyno itself. Let's continue with our animation. Now we're running the system. Again, dyno engine here. We are generating load and we are generating heat that's trying to be carried off. So now you can see what's happening is the red is denoting hot. The hot water is being discharged from the 3 accessories and also discharged through the dyno. And that water is running by gravity below grade again, and it's flowing across and into the hot side. You can see it. In this case, it is not dumping into the cool side. It is, the pipe is routed all the way across into the cool side in this illustration, or I'm sorry, into the hot side in this illustration. Now we're going to continue on with the cooling tower. So what's happening now is the hot water is being pulled up by this pump system here, and is being discharged into the top of the cooling tower. What happens is, as the fan is rotating and through the miracle of heat of evaporation process or cooling of evaporation process, the water is cooled and is gravity drained back to the cold side of the system. I'm hoping everybody can follow this. This is probably a very simple and smart method of seeing how these systems function. So I hope this is helpful.
Hey Rick, could we ask you a quick question? Mark asked a question: is are you using antifreeze in cold climates in this system?
Yeah, you can. As a matter of fact, if typically if you are using antifreeze or you have the option of using closed loop cooling for your engine, you can do that. You can run antifreeze through the system. That's not a problem. So that's typically done through the use of closed loop cooling.
Another question is, can PowerTest help users with the sizing of the water system, tower, pumps, and piping?
Oh yeah. So it's typically what we do is when you're looking at this view, in fact, the next page that you're going to see is one of our standard water circuits. Is once we determine specifically what you're looking for, and we need more than typical information of it's 1,000 horsepower, that's all I need. We need information as far as torque at speed, power at speed, etc. But we can help you with that. Once we find that out and we size the system properly and review it, once we get to the point of quotation for a customer, we typically provide a simple water circuit, and that's what we're going to look at next, which gives you data as far as flow rates, pressures, etc. So it's and for me, I handle international customers, so I've got to deal with bar, KPA, liters per minute, etc. So I have no problem providing any data you may need, and Celsius. So it's I'm sorry for what the crazy team in the U.S. did. We should have stayed with the metric system back in the early 80s, and unfortunately the inches and feet won. But I would much rather be in the metric system. I'm sure most of you aren't old enough to remember that.
Last question from Miguel has a great question. What is the percentage of water lost by evaporation on the tower?
Oh, that's actually a very good question, and I'm going to, typically you can say that 2.5% of the water that's passing through the system is lost to evaporation. So as a matter of fact, you can see down in this, I'm going to just, my cursor is looking at the hot side. What this is this line coming in is a line leading from the water utility. So, and this is a float valve here, denoting a float valve. So as the reservoir goes down because of evaporation or through parasitic loss, which we'll talk about later, this will replenish the system. So you have to replenish about 2.5%.
Okay, last question before we go on to the next slide, if you don't mind, Rick. When does it make sense to build a recirculation system versus continuing to use city waters to supply to the dyno?
Number one thing is cost. I think it's you have to remember once we can walk through. I'm trying to think about it, how I can answer that. By far the biggest payback is cost to the utility usage. If you have to pay for your incoming water and you have to pay for your outgoing sewer, that can get quite costly, especially in this day and age. So we can look at both methods, and I would say by far 75% to 90% of our customers do buy cooling towers because of the natural resource issue of using water now and having treated water. So it's by far the most common method of cooling.
Okay, great.
Did I answer that question, or was I acting like a politician and I evaded it?
You answered the question. Thanks.
Okay, so now we're going to walk into the next slide, and this might help everybody to denote what's going on. This is basically the same circuit you were looking at before, but with some information called out on it. This is a typical water circuit that we would provide you with a quotation to tell you what's happening with the system and what kind of flow rates. PowerTest, number one, can provide the majority of the components, all the major components, the pumps, the cooling tower, sizing of the reservoir, any of the accessories that I've got noted on here, we can provide, or we can tell you what you need and you can get those locally. So it's that is up to you. So it's everything is sized based on your requirement. If you're overseas, typically it's 380 volt, 50 hertz, 3-phase and 220. If you're in the States, typically it's 460, 3-phase, 60 hertz, and 110 single-phase, 60 hertz. So we provide the material you need for the pumping process, cooling tower, etc. on the system. But I think the big thing is this gives you an idea of what would be provided with a quotation. I'm going to walk through it once. So this is made specifically for you. And before I even send this out, we're going to we'd be talking on the phone and discussing what type of system you want, and we'll be kind of looking at that in a little later. But in essence, maximum horsepower, this is going to be specific to you and your dyno. So the dynamometer, we'll just say, for example, for us, I'm going to pick our model 35X06, which is a very big seller. That's a 2100 horsepower dyno that we produce. In that case, I would be entering 2100 horsepower up here, and typically I'm going to enter the same size as the dyno, but there are cases where people don't want that. So I can enter something that's less than that if you would like that. But typically, whatever the dyno sized for, we're going to say the engine will be sized for also. So those two are standard. Based on some calculations, I can take a look and I can indicate the minimum size of the reservoir, and that can be provided in both gallons and liters. Over here, as we walk through, we've got the cooling tower pump, and we will indicate on this drawing specifically the flow rate and pressure that you've got to have to operate the system. So here we go, we're walking up through the system, and here we're indicating wet bulb temperature, heat removal. In this case, remember we said 2,100 over here, and the same for the engine. So what does that add up to? My mathematician cohort, I know you don't know this because you're too good at talking in that math. So this is 4,200 horsepower. Inlet temperature, so that is the temperature going into the system. Typically that's recorded at 120 degrees F. And the discharge temperature, and the discharge temperature is directly related to the wet bulb temperature. And I think we talked about wet bulb before. Wet bulb temperature is specific to the location that you're in. If you have extremely high temperatures, your wet bulb will be high. If you're along a coastline, along the equator, your wet bulb temperature will be even higher, because not only do you have high temperatures, but you have high humidity. So let's just say, for the sake of saying, the wet bulb temperature is 21 C, which is approximately 70 F. My inlet temperature will be about 7 degrees warmer than the wet bulb temperature. That's how we size our system. So our discharge temperature will be, if we got 70 degrees F for wet bulb, so we'll be at 77 F for discharge temperature. And also, you can see we've got the sizing for the dyno and cooling pump here. So it's very inclusive, and we designed this specifically for your application. So very simple. And if anybody needs any information on this, at the end of the presentation, email me or call me, and I'll be glad to forward you to the sales guy in your area to help you. But if not, you would just want to talk to me because of my friendly voice, I will be glad to forward some samples of these circuits onto you. Now we're going to walk into another one, and I call this above and below grade water circuits. There are situations where customers don't want to buy a cooling tower based on cost. They can be pricey. They can't fit it in their location. There's no place for it, or money is tight. So there's other methods of doing that, and these are some variations on the standard process. In all of the cases that we're looking at, you could apply a cooling tower, you could apply a smaller cooling tower to the system. But in essence, what this is a non-cooling tower system, and we've got water stored via gravity below grade, and we've got a pump system to lift it to the top of the secondary reservoir. and then it's used for cooling or providing cool water to the dyno and the engine cooling accessories. The problem with these circuits is you can only run it the length of time that you have water for. So water flow rate is basically related to the load applied to the engine. Once the water gets up to a certain temperature, you're done. You can't run this any further. Let's take a look at this. So this is that same circuit as we're looking at it. Perhaps a little clearer on the layout on this device. I'm going to go to a secondary circuit. So here we've got the reason why we do this with the below grade is because in this case the customer wants to use gravity to drain from the dyno and from the engine accessory. So we've got a water storage reservoir that is below grade, and then he is taking it. So this is hot water, and typically what happens is if we start from the beginning, if this cold water reservoir is full, that means the below grade reservoir is empty. So what's happening when we start up the engine and we're about to operate the dyno, the water is being pulled out of the above grade cool water reservoir, and it is pumped through the system, and your runtime is limited by how much water is in here. So if you tell me I've got a 2-hour runtime, what I will do is I'll look at the maximum flow rate required for a specific horsepower, and I'll say, okay, we're going to size the reservoir accordingly so you can run for, if you tell me 2 hours, I'll size it for probably 2.5 hours or somewhere in that area. So what happens is as this reservoir is going down, water is obviously flowing through the circuit and is discharged into the below grade hot water reservoir. When this water runs out, we're done testing. So it's, for me, especially in hotter climates, I'd like to leave the water in the lower reservoir because the ground is typically cooler than the air. That would sit overnight, and in the morning when you're ready to run again, you can take that water and pump it back up to the top reservoir, and you're ready for dyno testing again. So relatively inexpensive system. You need either a polyethylene water storage device down below or concrete, and you need above grade polyethylene tank up on top for drawing the water out of. I'm going to move forward. And now we're going to look at one where this is much more common. Let's just say you're in a rented facility, or you can't do any below grade penetrations. So it's not as uncommon as you may think. In that situation, we've got a system where we can use 2 above grade reservoirs, and in essence a sump that's built into the bottom of the dyno subbase right here. So what's happening now is all of the water from the engine cooling column, the charge air cooler, the after cooler, and the dyno are discharging into the subbase. An alternate method is to actually have a small sump located. I'm just going to draw a little picture here right next to the dyno. In essence, what that is we'll have a sump-mounted pump that will pull that out. Excuse me, sorry. That is an alternate. So if you have no way of penetrating the floor, we may be able to do a sub-base with water inlet and water discharge, as I've got indicated here. But you can see what's happening on this one. Again, this is no cooling tower, so limited runtime. And what I'm doing here is, as the hot water, and we didn't illustrate this, but basically what the circuit is as the hot water comes into this small reservoir below the dyno, a pump is taking it, and it either can push it either this way or this way, depending on what direction this valve is placed. And the beauty of the valves is we'll just assume for the sake of discussing this that the hot water is going to go this way. So the water is going to go up, discharge into this reservoir, and continue flowing. Meanwhile, the water over on this side, which is holding the cool water, the water is going through the circuit and into the dyno circuit, flowing into the dyno and also into the cooling circuits. The beauty of this is you don't have to basically do anything with pumping fluid or water from one side to the other. And why I'm saying that is by the use of these three-way ball valves, you can change direction. Either I can pump the hot water into this one, or if we get a reverse direction, I can pump the water, as you can see by the second line, over into this one. And the same thing's true with the dyno cooling supply pump system. Either I can draw it from this reservoir, or if I reverse this valve, I can draw it from that reservoir. So again, we're back to the same thing as the circuit we looked at previously, which is limited runtime without a cooling tower, but it is an inexpensive method of running a dyno. And let's see here. Power test DCI, and I just want to get into this a little bit because this is a learning experience and for people, and basically what I want to talk to you about is what we call DCI, which is design, construction, and installation. In essence, I want you to think about this. You guys are typically experts in testing engines and servicing your customer. You're doing this day in and day out, 24/7. What I find is I talk to customers every day, and they say, "Don't worry about it. We'll handle the installation of the dyno." And what we find is the customer is an expert at their engine testing, their engine rebuilding, and working with their end user. But they are not experts at doing installations on one of these systems. So I never quite understand it. I know that there's a value to every dollar, but to become an expert on something you're only going to install once, the value is lost on me a bit. So what we do is we offer the service of supporting you on that. So not only do we supply the dyno experience, but we can also supply various levels of support for you for a dyno installation. That can go from a simple drawing set that basically you can utilize in conjunction with your contractor and subcontractor to any variant, all the way up to we install the entire system. We provide everything. We provide all of the subcontracting. We supply one of our team members on site to supervise the system and provide reports. And backing off a little bit for some of our international customers, we provide on-site service with our DCI manager to work with your subcontractors because it is difficult and a challenge for us to work with contractors outside of the country. So it's we've got many different variations that we can work with, and that's our job. We've got a lot of experience on test cell design and dynamometers. That's what we do every day, as what you do every day is rebuild and test engines for your customers. But that's about it for me. I hope I didn't take up too much of everybody's time, and I hope that everyone's learned a little bit. I hope I'm successful in that respect. I appreciate your time, and again, if you need anything, my name is Rick Ballo. I'm the International Accounts Manager for Power Test. You can see my email address down below, which is rickb, R-I-C-K-B, @pwrtst.com. I think I'm turning this back over to my associate, and I think we're all finished.
Yeah, and everybody, if you could just do me a favor, send in a quick word or two of your impression of the webcast, because we're going to be doing these on a monthly basis, and we want to make sure that we're resonating with what you're looking for in the marketplace. And I think if everybody could just put in 1 or 2 sets of feedback, that would really help us, because we want to not make assumptions. We've answered a lot of questions. Oh, good, a lot of people saying great job, awesome. But I think that's just something that we want to make sure that we're ascertaining, your feedback, so we're working in conjunction with you. So we want to thank you. Everybody have a great weekend. It is a lot of information. We are going to be recording today's session. The other thing I'd like to do is make sure that you all know that we will be recording and distributing this to you along with a handout. And if there aren't any other questions, I want to thank you for your time, and everybody have a great weekend.
Say, Tim?
Yes.
Tim, this is Rick speaking one more time. But more than anything, I want to make sure, number one, I wanted to say the people that said awesome and great job were probably my children and my wife, number one. But number two is I want to make sure that what I presented to you is what you want. And is that what you expected? Did I satisfy your requirements for learning about water circuits? I think Tim said it, but maybe I'm reinforcing it a bit. We want to make this so you can learn. This isn't about buying and selling. This is about learning. So we're trying to help you make the right choices with your dyno installation. And I'm turning it back over to Tim. Thanks, Tim.
Yep, well said. Everybody have a great weekend.